we're going to talk about some financial stuff in this section.
Word, Holmes.
This is some real life application-y stuff. This can change your future.
Get you some bling.
Yeah, so we're going to talk about just first off your interest compounded annually. Now, this is
by the way,
fabulous.
I think this is super interesting.
Okay.
Probably the most applicable lesson.
The one you need to hear about most, right?
The most, yeah.
Because here's the deal. Whenever you take your money and you put it in a bank,
right,
then you have a lot of different options of how you can put it in the bank. But one
right.
option is to put it into like a savings account or some kind of an investment.
Right.
And when you do that, you want to look at the interest rate that they're offering you and how often it's compounded. And you definitely want it to be compounded,
yes, not
uncompounded.
Right. You want compound interest on any account that you want to choose for an investment.
Because here's what that means is, let's say you put $1,000 in,
right, and
it's compounded every month or whatever.
Ooh, okay? Monthly.
Yeah.
Wow, nice bank.
At the end of 1 month, they give you the money for the interest. They add it to that $1,000.
That's right.
Then the next month, they don't calculate the interest based off the 1,000. They calculate it off the new amount.
Right.
So that means your interest gets interest. And the longer you have that investment in there, then the better off
you can be.
That's going to be.
And we're going to look at a lot of different lessons inside this unit here that deal with some of that. So.
Yeah. Yep, definitely.
It's going to be very interesting.
Yeah, the formula for simple compounding is that A, which is our
total amount, the amount that we are going to have when we're done.
Yeah, equals P, which stands for the principal.
That's the amount of money you give the bank to get started.
Right, and then in parentheses you put 1 plus R, which is similar to that exponential form that we talked about. And
the rate in this case is going to be the interest rate, so it's going to be
a decimal.
Some sort of decimal.
Yeah. And then it's raised to the n, and n is the investment after in years.
Right.
And this is specifically if we're compounding annually.
Right.
So we're compounding once per year, so this is the formula that we would use.
Right.
So let's just plug that in.
Let's just do it. You'll need a calculator for a lot of these because the decimals can get wanky if you try and do it.
And typically big numbers and stuff like that. So don't be afraid to use your calculator. So this Madigan character invests
what a character that one
500, too. That's the principal. At 7% interest, so you change that to 0.07. It's compounded annually, so we know that means that we're using this formula. Find the value for investment 10 years later, so we put 10 where n is. We just plug that into our calculator, and what do we get?
$983.58.
$983.58.
And that's without ever adding another penny. You've almost doubled your money.
Right. That's amazing. So...
And all you started with was $500.
Yeah, so the after 10 years of just letting it sit there, the bank is giving you for free $483.58. So that's pretty awesome.
That is pretty awesome.
Okay, so the way this changes if you're not compounding by year is it just changes
several times per year.
Yeah, it just changes a little bit. So I'm going to write the formula right here. What happens is you take K, and K is how many times per year you're going to compound, and it gets
usually
introduced.
It's like you see it like biannually, which K would be 2, and you see it quarterly where K is 4, or monthly where K is 12. But it's how many times that we're running the numbers.
Okay, so how many times it gets compounded. So in this particular example that we've got on example 2, we still have an annual interest rate, but we're compounded monthly, which means, if you think about it, how many times a year would you get money if it's compounded monthly? 12 times a year.
12 times a year. There's 12 months in 1 year.
Yeah, so that's K, this is N, this is P, this is R. We just plug it in.
Pluggy, wuggy, chuggy, smuggy. And
almost forgot to put over 12 there. That was a close one.
You need to have over 12 there.
Now, make sure that when you're plugging this in, that you put either put parentheses around it or multiply it out yourself. Like type in 60 or put in parentheses if your calculator doesn't automatically give you like a little box for your exponent.
Because otherwise you'll do to the 5th power, and then whatever you get
for
a total answer will be times 12, and that's no deal. So $782.84.
All right, $782.84.
There you go, Shaka Khan.
Oh, look, there's the formula. It's
Hey,
right there.
hey, we were just one step behind
Yeah.
or ahead.
Yeah, I don't know what happened. So,
You got to be careful with your chains. They're starting to have a tear. Your bling.
okay, thanks. Example 3. Marin has $500 to invest at 9% annual interest compounded monthly. How long will it take for her investment to grow to $3,000?
Oh, they don't give us a T here.
Yeah, the PR monthly means that K will be 12.
Right.
And we're trying to figure out when A will be 3,000. So if we set that up.
Basically, this turns into a logarithmic style. It goes from being an exponential type of problem to a logarithmic problem. Why, you might ask?
Because our variable is in, the exponent.
You were supposed to ask.
Oh.
But that's okay. So yes, so we've got to get it out, and the only way to do that is to get a logarithm written in. So first order of business is get rid of everything not inside or belonging to or part of being raised to a power.
Right. So 3,000 divided by 500 is 6. And why don't we go ahead and do this? 1 plus 0.09 divided by 12.
Okay, hold on. 3,000 divided by 500.
No, you don't need to do that part. I already know that part.
Oh, sorry.
Do the parentheses.
1 plus
0.09
0.09 divided by 12.
divided by 12.
I get 1.0075. Now on this, it's possible you could have a pretty tiny decimal, and you really do want to try and keep as many of those decimal places as possible.
The more the merrier.
Indeed, it's like a party. The more people that show up, the more fun you're probably going to have.
Now let's rewrite this as a logarithm.
Okay, good plan.
So we're going to have log with the base of this exponential expression. So 1.0075
Yeah, it's going to be really weird.
Of 6, because remember we go in a circle here to figure out what to put in our equation, 12t. So we can figure this out on our calculator. Either your calculator will set up the template for you and you'll just type it in, or you would do log of 6 over log of 1.0075. And after you do that, you just want to make it divide that answer by 12 on both sides, and that will give you t.
Yeah, try not to round anything on that.
With a minimal amount of rounding.
Right. So I get 19.98 years.
Hang on one sec. 19.98 years. That's about 20 years.
That's about 20 years. Pretty close. That's like December 30th.
Yeah. All right, example 4. Jasmine has $500 to invest. What annual interest rate compounded quarterly is required to double her money in 10 years in 5 years?
So this is going to be one of them solving backwards logarithmic type of things.
Yes, and we're still going to use the
I'll be right back.
the same kind of formula that we've been using for example 3, but now we actually know what amount we want to get to, because how much do we have if we double $500? We'd have $1,000. So that means that A is going to be 1,000, P is going to be 500. We're trying to figure out what the interest rate will be. We're compounding quarterly, so when you think about K, you need to think about how many times do we get interest in a year. For quarterly, we would get it 4 times, so we put 4 down there. And then to the KT, we put 4 and then 10, because that's how many years we're talking about for the first time. We'll solve it once and then we'll do it again by replacing the 10 with a 5.
Right. Remember the KT part, the exponent, needs to be the total number of compoundings that occur while you're earning your money or doing your whatever.
Absolutely. So divide by 500 on both sides, and that gives us 2. And that should happen because we're trying to double here. Now let's think about how to solve this. What would you do here? This actually isn't necessarily a backwards logarithmic thing. Our variable's not in the exponent. We can actually do this a different way.
Yeah.
The 40th root.
Yeah, you could take the 40th root, and then what that does is it gets rid of that exponent of 40. Now, 40th root is not necessarily something we're going to, it's not something you think of right off the bat, typically.
Right. So on your calculator.
Okay, so what you're seeing right now on the side is the calculator, and we're showing you how you can use the 40th root. And there's 2 different ways to do this, and they're both pretty easy. So just, if you have some issues, just check out what we got going on the side. But it's not too hard, and I'll just punch it into my calculator right here also right now. So that would be the 40th root of 2. So 1.0175.
Shh, we're recording.
That was not an angelic escape either.
Why did I write 10 there? I'm sorry, that's supposed to be a 4. That's a 4 on the bottom. I just randomly
Right,
wrote.
4. So now go ahead and subtract 1 from both sides.
So that gives us
0.074 or 0.075.
equals r
Yeah.
over 4. So then
Yeah,
you
no,
times
no.
by 4
Right,
on both sides?
Right, times 4. So I get 0.0699, and that should be our interest rate for this particular problem.
And we would change that to a percent.
Right, 6.99%, and that sounds like an interest rate that would work. Like if we got an interest rate of like 2,000,
That's a bad idea.
I would arch my eyebrow.
Yeah. So kind of running out of room here. All we do for the second one is you put 5 everywhere, where there's a 10 right here. And then you solve it the exact same way. And so what does that change? When we work it out, it just changes a few of the numbers that we multiply or divide or
Right,
whatever.
right.
So it's still,
So it's still the same
4
process.
times 5. So instead of the 40th root, we're going to take the 20th
Right.
root of 2.
Right.
And then
And
after we take the 20th root of 2, we have to subtract 1. And you can work this out in detail if needed. And then after we subtract 1, we'll have to multiply by 4.
Right. So we're going to do all of that, and we're going to end up with 0.14105.
And that makes sense that would be a much bigger interest rate to have to
To get to the same amount of money.
in half as much
Right,
time, right?
right. And basically, that's almost a doubling. It's a little more than a doubling, but
Yeah.
that would make
we almost
sense.
doubled our doubling.
Right,
Yeah.
right.
All right, now we're going to talk about compounded continuously, which is awesome for 2 reasons. One, in real life, that would be the ideal situation because that means that every moment of every day you're earning interest and that's getting added to your balance and then you're earning interest on that balance. Because if you were to do a problem where you changed how often it was compounded, the more it's compounded, the more often, then the better that is. So, and it's not a huge change most of the time between them, but any little bit helps when it comes to money, right? So the other reason I think it's awesome is because it has like the simplest formula ever. A equals P e to the RT, or PERT, you could call it if you wanted to. So on example 5, suppose Scott invests 500 at 8.5% annual interest, compounded continuously. And this word right here is how we know that we're using this formula and not the one we've been using. So find the value of the investment after 1 year, 3 years, 8 years, 45 years, which this is all just going to be really easy plugging in, right? So the principal is 500. E is a button on your calculator, remember. The interest rate is 0.085, and then I'll leave this as T. What we're going to do is plug in 1, 3, 8, and 45 and see what that gives us. So get on your calculator, type 500, and then find the E to the X button over on the left side. Second LN is what it is on most calculators, and then put 0.085. We're going to do times 1 for the first one. And since this stuff is dollars, we typically want to round this to 2 decimal places, so because that's how many cents there are. So for 1 year, that gives us 544.36. Then just go up and change the 1 and make it be 3. So that gives us, welcome back, Mr. Hazelwood,
Thank you. Got distracted.
645.23. And then go back up and change that 3 to an 8. Did you just tweet me?
No, gotta try and do this. Oh, I didn't get it. There we go.
And then change the 8 to a 45.
Well, that was a pretty good picture. I don't know if you saw that.
No, I
Sorry.
didn't.
That's more like it.
We're just recording here, so that's okay.
Okay, annual percentage yield, sorry, that's misspelled, is the percentage rate that if you compounded annually would yield the same return as the given interest rate with the given compounding period. So that sounds kind of complicated, but basically what we want to do when we find the annual percentage yield is we're talking about if we have that $2,000 that we're investing and we say, what about what will happen after a year? So we're going to put a 1 plus X in, and then on the right side, we have 2,000, 1 plus the interest rate,
Compounded quarterly.
so over 4. Okay, and then our time is we're talking about after 1 year.
So
what's
we're
going to happen.
just going to have 4 for the exponent.
So it's going to be 4 times 1, which is 4. It looks great.
That looks
It
awesome.
looks totally disgusting.
Yeah. Okay.
yeah.
Epic, actually.
Okay, so but this 1 plus X over here has to do with basically that's the percentage
That we're trying
that
to
we're
be.
trying to get.
Right. The actual yearly percentage as opposed to compounding 4 times.
Right. Okay.
Right.
Okay. So to solve this out, we would. This is just a number that you just type into your calculator.
Yeah, you just put it in there.
Figure it out.
I will number it up right now. The 2000s, by the way, they're Dunskies. They're
Oh
out of
yeah,
there.
because you could divide both sides by 2,000. That's just super convenient.
Super indeed.
So that's 1 plus X equals that number that Mr. Hazelwood's finding right now.
Doing it right now.
1.0525
Yeah,
minus
and then
1.
and then minus 1. And so the actual annual percentage yield,
is 0.0525.
the equivalent to compounding 4 times a year.
Yeah, so yeah, if we wanted to do 5.15% annual interest, but we're compounding it quarterly, that's equivalent to just having 5.25%.
Right, just one time a
that
year. Right, you'll
So-
get the same amount of money after the same amount of years.
Exactly.
Yeah. So Rose trying to determine which investment's going to be better.
Right after she got back from the Titanic.
Yes.
Yeah. Okay.
Save me, Jack.
You're my only hope.
You're my only hope, Jack.
Okay, so explain what we're gonna do on this problem.
Okay, so what we're going to do is, if I can just avoid from kicking the camera, what
Oh
we're
no,
going
an
to do.
earthquake.
Earthquake, another one. We're going to actually convert these to annual percentage yields. And one of these will be larger than the other.
Right.
And because we're, like off the previous example, the principal does not matter.
Right, because remember the 2,000 just
They
canceled
just
each other
canceled.
out.
Right. So basically we're going to have 1 plus R, or X, okay, is equal to,
The P cancels out with
cancels
that
out.
other thing.
So it's going to be the just the inside part, 1 plus the rate over the K,
which will be 4
which
because
will be
it's
4,
quarterly.
and then it's going to be
4. And we're just going to do a year.
right.
Right? So
It's
4 times
right
1.
by the, there you go.
Okay, and we're comparing, we can figure out what that is, and we're comparing it to the other model,
Which is going to be 1 plus X. We could probably say Y if we wanted to differentiate as well, or you have a different color.
Oh,
So-
right, yeah. Y. Let's do
So
Y.
okay,
And this one's 8. Okay, this one's just
just
8.7
Yep,
over
monthly,
12,
which will be 12. Yes.
and that'll be 12
That'll
up
be 12 up there.
So
So-
we figure out what these are, and we're trying to figure out which one will
Two
give us a
separate
bigger
things.
number.
Right. So we're just going to punch all this in.
And remember to subtract the 1 over on both.
Right. So I'm punching in the top one right now, 0.0875 minus 1. And I get 0.090%, 0.090.
And that's the decimal, so
That's
that's
the decimal version. So that's
9.0%.
9.0%. Okay.
And for Y,
And for the other, for Y, I get 1.091.
so the first one had a
So-
4. This was a 4 right here. This one has 0.5. So that is super close.
Super close, but if I am looking for an
That's
investment,
a 0 because I
then
subtracted 1.
I'm going to go with the one that's compounded monthly, even though it's a little bit of a less interest.
Yes, exactly. So interesting problem
Yeah,
there.
interesting indeed.
Now this is where it gets a little more complicated,
But also super applicable.
yes, now, because really, yeah, you could take like a sum of money and put it in the bank and let it sit there for 10 years or whatever and see what
Right,
happens.
right.
But ideally, what you want to do is put money each month into an account.
Right, like
that
a Roth
earns-
IRA.
Yeah, like for retirement and things like that. And when you do that, if the earlier you start, the
better
better
off you're
you'll
gonna be.
Because eventually you could end up that the interest you're getting each month is enough like to live off of.
Yeah,
And
but
that's
not
like,
immediately, but like 30, 40 years down the line.
Exactly. So so that's for future value investment, where we have R is the payment you're making
Right.
each month. This I for these is the
It's a little bit weird.
yeah, the I is the interest rate per compounding period. So
Right.
that's going to be R over K.
Right.
And then the N is going to be the K times T.
Which is
Because
the
it's-
number of times this happens.
Yeah, the number of times in a year that we compound or
Right.
whatever.
So if you do something like a Roth IRA, and I believe as soon as you get a job, you can contribute to a Roth IRA.
Yeah.
And you would contribute monthly. This is a formula that you could use to figure out how much money you would have.
Yeah, like
down
if
the
you
road.
had a goal that by the time you retire you want to have so much
Right,
money.
right.
Yeah. So in this example, at the end of each quota, sack of quotas,
I got a sack of quadas.
quarter year, William makes a $500 payment into
All
the
the typos
Hazelwood
are.
Mutual Fund. Who's this guy William that's contributing to your fund?
That would be my son, Rowan William.
Oh,
Yeah.
okay. If his investments earn 7.88% annual interest compounded quarterly, what will be the value of William's annuity in 20 years?
Right.
So this is future value, so we do future value. The R is the payment, so that's
Right.
500.
$500 4 times a
It's
year.
not really what I meant to do. Times, and we've got this big fraction where on top we've got 1 plus I.
And then the interest rate
So that's the interest rate
over the number of times we're going to do it each year.
And it mentions quarterly.
That's
so.
4. Quota.
And then the N is 4 times, we're doing 20 years.
Yep.
Minus 1. And then on the bottom, 0.0788 divided by 4. So the tricky part of this is one, we're going to give you the formula for this, but you have to remember what I and N are.
You got to put it all in. And if
And-
you can use the template on your calculator, that will help just tons.
Yeah, it is kind of tricky to get this plugged in right, but if you have a calculator that'll do fractions and make them look pretty, then you just literally make it look like it does, the way we have it written here.
Is that I Dream of Jeannie tune there?
Yep.
Do-do-do-do. Boo.
Would you focus on typing?
I
I'm just
am
trying to fill in
typing.
the
So
silence.
2 guys walked into a bar. The third guy ducked. Wow, that's quite a hefty little sum over 20 years there. $95,483.39. Now,
Now-
can we just take a little quick side note here?
And compare.
Let's just say, how much money did we really invest?
Right, so $500 each month for 20 years. So 500 times 12 times 20.
That is, I've got an error.
What is-
Something's wrong.
How did that look? That's not right. What'd you do wrong?
0.078 500 times.
Oh, not 12 times 4. 500 times 4.
Oh, shoot. Okay, yeah, there we go. Okay, yeah. I was like, no, our math is good. Our math is good.
No, it's not.
Now it is. We only invested $40,000
Wow, so that's $55,000
extra that we didn't have to do anything for.
That's amazing.
That is amazing.
And before I switch this off, the present value is talking about a loan. So future value talks about an investment. Present value talks about a loan, where if you're doing like a mortgage or a car
Buying
payment,
a car,
R then is the payment you pay each month,
right?
and ends up giving you,
How long it would take to do that.
yeah. This is where that present value formula is going to come into play.
Right, and basically what we're going to do is we're going to buy a car. Rose is going to buy a car. She's going to drop $18,500 on it, and she's going to have monthly payments for 4 years, and she's going to put $2,000 down.
And this is the interest
And
rate.
the interest rate is 2.9%, which is basically right now kind of a realistic interest rate.
And we want to know about the payment,
Yeah, what's
which
the
is
payment
the
gonna look
R.
like?
So that means they told us the PV part.
Right.
Its present value.
That's how
is
much we currently owe.
18,500.
Well, we owe 18,500 minus 2,000 because
So
So
we
we-
put 2,000 here, or do
yeah,
we?
we put 16,500 because we have lowered our total financing
Okay.
of the vehicle
Okay.
by $2,000.
Sure.
Or we don't know. So and then times now.
And this is a different formula.
It's the same formula actually, but the one is in a different place. So instead of being
And
minus
there's a
1 at the
negative
end,
in the
right,
end.
right. But it's going to be the same process. The I is the same thing. That's going to be that N and K business. All right, and then your exponent will be negative. Okay.
Monthly payments.
Monthly
so that's
payments.
12.
That's going to be 12, and then our exponent's going to be 12 times 4 because we're going to do it for that many times. And then on the bottom is the 0.29 divided by 12. So this is our setup on this guy.
So we have to figure out what this is. This is all just a number. And then once we know what that number is, we just divide it into 16,500 and we'll know what R is. Easy
And
peasy.
And again, if you have the template version on your calculator, that can sure make the easy peasy even easier peasier.
Hey, did you know that 3.14% of seafarers are pirates?
That's
Get it?
that's
So,
okay.
it's,
Go
do you know,
on.
Do you know what a pirate's favorite math formula is? R.
Arr.
That's not a formula.
Oh.
It's pi r squared, or maybe 2 pi r. Yeah, one of those two.
Okay, so on the I get 16,500 is going to be divided by 45.269.
Right. So
Yeah,
that's
there
what
you
we're
go, there you go,
dividing
there
that
you go.
into it.
So, okay, Steve, you're one step ahead of me there, and it's all good. It's all good. So, our payment, and
R
this,
equals.
having made some payments myself, I feel like this is pretty correct. $364.49 each month to pay off your car.
Awesome.
Yeah, so there you go.
Bye.
I got this student Chuck, and he and I are in a contest to see who can earn the most money by the time I retire. Okay.
Okay.
So we're both going to contribute $200 every month to an annuity that earns 12.5%. Now,
Okay.
believe it or not, this is a true story. You can actually find an annuity that earns that much. I know it sounds crazy.
It may be a little difficult these days, though. The interest rate's really low.
Yeah, but I've got several that are earning double digits.
Amazing.
So Mr. Hazelwood started his annuity when he was 30 because, college, getting married. So I started when I was 30, $200 a month every month. How much money will I have when I retire at the age of 65?
Okay.
Part 2. Chuck starts his annuity when he's 18. He lives off of ramen noodles and rice all through college. He waits to get married and have kids, and he does all that after he's 30. Then he quits putting his money in, and he just lets the principal grow on its own until he retires at 65. Who's going to have more money? Me, the guy that puts it in a lot longer, or Chuck, the guy that puts it in a lot less?
Okay.
So
So
that's what we're going to look at.
this is a future value problem.
This is a future value problem.
And the monthly payment for both is going to be 200.
It's going to be the same. It's going to be 200. Everything is going to be the same except for the time. And the time is going to be different for both.
Okay, so
So-
we have 1 plus 0.125. How much is it compounding monthly?
It's monthly. It's every month.
And that'll be to the n, which will be 12 times. The first one is what? Third
So 30 to
start at
65.
30, so that's 35.
35. And then minus 1.
minus 1, and then 0.125 over 12 on the bottom.
Now, mine is going to be the easiest one to determine because we just plug it into this
And then
formula.
that's the amount you'll
and
have
that's
when
the
you
amount that I'm
retire.
going to have.
Chuck's
So
going to be a little bit
Chuck's
more
going to be a little bit more complicated, but not overly so. So let me just punch what I'm going to have in here.
Difficult
so
Chuck.
1
It's always more
plus
complicated.
0.125 12 to the 12 times 35 minus 1.
Now, as he's doing that, as I set up the second formula, notice that he contributes from 18 to 30, so that is 12 years times the 12.
Ooh, wow. Wow, I'm going to be so rich, it's not even funny. $1,471,917.
But you're a teacher.
$1,471,917.08. That's
And
baby got bank right there.
Okay, so the difference then for Chuck is that he only contributes for 12 years, but once we're done, we can look at how much it's going to grow from the time he's 30 to 65. So
after 12 years, Chuck has $66,183.39.
but basically he's going to take that and make that the principal for a new, and it's kind of like he's taking it and making it the principal of a new investment.
Right.
But
And this time it's going to be 1 plus that same interest rate. Still,
all the rest of that's
going to be the same.
But now he's going to do that from 30 to 65, so that's where the 35 is.
Right.
So this is where it's really going to get mind-boggling.
It's going to get. You will be amazed at the difference.
You promise?
Yes.
Does that say 5 million?
Yes. $139,957.63.
You forgot the dollar sign.
That's the power of compounding
Times
interest
that
right
by
there.
like 0.05, just for funsies.
Times 0.05.
So then at the end, if he took that and put that in a savings account that just earned like 5% interest, every month he would make $256,997, which is more than enough to live on.
More than enough. So
That's enough to live on and buy a car every month.
yeah.
A
So
nice
that's the
car.
power of the compound interest. And this, by the way, is a true story. Like this could be a true story for you.
Yes, if you're Chuck, you could be Chuck.
If you could be Chuck right now, if you're watching this and you're in high school, you could be Chuck.
Okay.
Okay, all right, sounds good.
Okay.